Okay, let's look at this problem. A metal cube is 2 by 2 by 2 inches, and when heated up, its side length increases by 0.021 inches. Use differentials to approximate the change in volume. I want to do two things here. I want to go through this quickly and do it like I would do it if it were a test problem. And then after I've got the answer, I want to go back through and explain what the different bits of it mean. So we've got a metal cube. We know the formula for volume of a cube is x cubed. If we take the derivative of v with respect to x, you get 3x squared dx, or not dx, just 3x squared. And then if we multiply both sides by dx, then we get dv is 3x squared dx. So now I just need to plug in the values. X is the length of the cube, and dx is the change in the length. So dx is 0.21 and x is 2. So that gives me an answer of dv. Remember, dv is the approximate change. That's exactly what we want. So it's 3 times 2 squared times 0.021. So 3 times 4 times 0.021 gives me 0.252. And that's my answer. 0.252 cubic inches. And if I were doing this as a test problem, I'd be done. But let's talk about what's going on here. Specifically, I want to talk about sort of the geometry going on behind this over here. When we start out, we've got a cube that's 3 by 3. So it looks like this. And then when the thing expands, what happens is, in all three directions, it's going to grow. So if you think about what happens, that means on the, let's see, I'm gonna draw it like this. That means that from front to back, it's going to grow just a little bit. From side to side, it's going to grow a little bit. And bottom to top, it's going to grow a little bit. So we wind up with this. The differential is actually computing what those three purple blocks that I added onto this cube are. If you look at each one of these purple blocks, which I've purposefully drawn them where you can only see little parts of them, but each one of these things is a square. It's a square that's 2 by 2, and then the thickness is 0.021. So if you add up the volume of those three things, what you've got is exactly this up here. You've got three of them. They're 2 by 2, and then they're 0.021 thick. So that's what we added on here to get the differential. Now this is an approximation because the way I've got this drawn, it's not really how the thing expanded. It really would have expanded into a bigger cube. So, it would really look like this, where the bigger cube has this for its outside. So it's a bigger cube like that, but the differential doesn't take into account sort of the corners there. The corners wind up getting kind of left out. So anyway, that's where the differential comes from. That's why it works. All right, let's look at another example. A circular disc is measured as having a radius of 21 millimeters. And then it says the caliper used to measure it has a tolerance of 0.1 millimeter, meaning that the error in measurement is at most 0.1 millimeter. Find the approximate error and maximum and minimum possible areas of the disk. Okay, so let's see, we got a disk here. The area, of course, is pi r squared. And so the area of the disk, if the radius is 21, the area is pi times 21 squared, which is 441 pi. So that would be the exact area of this disk if the measurement was completely accurate. It would be 441 pi square millimeters. So we've got a circle that looks like this. However, it's saying that tolerance is 0.01 millimeter, which is pretty small. But 0.01 millimeters, that means that instead of the radius going from here to here, it might be slightly longer or slightly shorter. So what that means is the area might be off by a small amount. If you take this and I want this to go around the outside. I'm going to try to keep it on the outside of the circle. So if I take this right here, the width of this from one side to the other, that's supposed to be 0.021. That's the biggest that error could possibly be. And I'm going to do the same thing on the inside. Wait, that's the wrong tool. I want this. On the inside, maybe the error is here. So if our measurements are perfect, then the area is the area of the actual circle. If the measurement is a little bit big, then that means that we might have an error in that we included some of the purple. And if our measurement of 21 millimeters was too small, it means we might have lost some of the green part of the actual circle. So what we want to do is find the possible error in the area, and add that and subtract it off. Because the first thing it says is find the approximate error. All right, so area is pi r squared. dA/dr then is going to be 2 pi r. And so dA is 2 pi r dr. Now what that is, that's the approximate area of both of those highlighted circles. Because this is also 0.021. Now you might look at that and say, well, one of those is bigger than the other one. Doesn't the purple one have more area than the green one? The answer to that is yes, of course it does. It's the way it's drawn, it's a bigger circle. But we're talking about approximations here. This dA, the change in area, this is just dA. I need to be careful with how I say that. We're looking at the change in area, and dA is just an approximation of that. So really what we're going with here is that the purple ring and the green ring, they have approximately the same area. So let's see. That area, dA is going to be 2 times pi. R is 21, and dr is 0.01. So let's see. 2 times 21 times 0.01. That's 0.04. No, it's 0.42 pi. And I'm going to leave the pi on there just for ease of writing. So this is my possible error. And so the maximum area of this disk is going to be 441 pi plus 0.42 pi. You know what? Well, I'll just leave it like that. And the minimum area is 441 pi minus 0.42 pi. And these are approximations. And I could easily stick it in my calculator and get a decimal approximation. But anyway, that's what this does. It lets us say, given a potential inaccuracy of 0.01 millimeters in the radius, we can say that the area of this thing is in between these two numbers here. All right, that's the last example. So that's the end of the section.